All right, our video series here is going to be introducing you to eigenvalues and eigenvectors. And the first thing that I want us to do is actually define what these are. So an eigenvector means that there is some non-zero vector. And it's true that A times that vector is just a scalar multiple times the vector. So if you think back to when we did transformations, which was A times X, right? That transformation is just multiplying by a scalar. So if you have some vector, okay, and you apply A to it in that transformation, that transformation, all that it does is just makes it larger in scalar. So just dilates it, if you will. And then we call the scalar that does this, we call that the eigenvalue, okay? All right, so let's look at an example here. So let's say I have A and I have vectors U and V, and I want to just review for a minute how to find those transformations. So let's do A times U first. All right, when I do that, I get -3 minus 2, so I get -5, and then -1 plus 0, so -1. So originally, this vector U is at -1, 1, and then when I multiply by A, when I transform U by matrix A, I go down to -5, -1. Now, that's not just a reflection or a dilation of the original vector. That's a full transformation in the R2 plane. So by definition of an eigenvector, we would say that U is not an eigenvector of A, okay, by definition there. And I didn't ask us that in this problem, but I'm just helping make some connections for you as we're like learning these new definitions. All right, A times V. So in this case, I get 6 minus 2, which is 4, 2 minus 0, which is 2. Now notice that is a scalar of V, that this is equal to 2 times V. And if I were to graph that, I would actually have a situation kind of like what I have up here. So that means that V is an eigenvector of A, and the corresponding eigenvalue is 2. All right, let's do another set of examples. In this one, it's wanting us to verify, are U and V eigenvalues of A? Well, if that's the case, then A times U needs to be something times U. So let's figure that out. Like, is that true? So A times U. That ends up giving us -24 over 20. And we see that that's -4 times U, right? So yes, U is an eigenvector, and the eigenvalue associated with that is -4. Let's look at A times V. All right, if I do A times V, I end up getting -9 times 11, which is not equal to some scalar times V. So V is not going to be an eigenvector. In the next example, it wants us to find, or show, excuse me, that 7 is an eigenvalue of the matrix A. So let's think about how we are going to do that. If 7 is an eigenvalue, then I know that A times some vector x must be equal to 7 times that vector. Now, this is going to be true only if we have a non-trivial solution. So let's say if that's the case, then A times x minus 7 times x must give me 0. And so I can factor out an x, and I don't know the size of matrix A, so I'm going to say that A minus 7 times I, where A and I are the same matrix, just to make sure that I get that scalar multiple on the diagonal correctly, that is then equal to 0. So let's do A 1, 6, 5, 2. Let me double check that I've wrote that down correctly. 1, 6, 5, 2, yes. Minus 7i. I guess in this case, I do know that A is a 2 by 2, but just in general, when you use this formula and use these steps, okay, you'll always do those steps to figure out, to show eigenvalues and then find eigenvectors, okay? Okay, so 1 minus 7, negative 6. 6 minus 0 is 6. 5 minus 0 is 5. And 2 minus 7 is negative 5. And I want to try to figure out, right, the solution where this is equal to. Well, if I end up augmenting this matrix with 0, I end up getting 1, negative 1, and then zeros here. All right, so then if I let x2 be free, right, then I know that x1 must be equal to x2. And so my x vector, where this is the case, must be x2, x2, or x2 times 1, 1. Therefore, there is a vector that when you multiply it by 7, okay, you end up getting the same thing. So we get, if we take A, let's go back up to what we did here. If we take A and we multiply it by that x vector, that's going to end up giving us 7 times that x vector, okay, is what that means. So eigenvalue of 7, yes, and my eigenvector must be 1, 1. And so 1, 1 is an eigenvector of A, and the eigenvalue associated with that was 7. All right, let's look at one more example, I believe is what we have here. Oh, no, 2. Okay. An eigenvalue of A is 2. Find a basis for the corresponding eigenspace. So we're going to set this up the same way we just did before, where we know A minus 2i times x must give me 0. Okay, and that comes from, again, that ax must be equal to 2 times some vector x. I can subtract that over, setting it equal to 0, and factor out your x vector. And so this is going to help us find that basis for what we were going to call the eigenspace. So let's do A minus 2i And when we do that, we get 2, 1, negative 6 in every single row. Or 2, negative 1, 6, excuse me, in every single row. So if I augment that with 0, right, then I know that x3, these are all just going to be repeated, so they're all out. So I know that x3 is free. I know that x2 is free. I also know that 2x1 must be equal to x2 minus 6x3. And so maybe I'll write it up here in this space. x1 must be equal to 1/2 x2 minus 3 x3. All right, so let's write our solution vector for that space. 1/2 x2 minus 3x3. x2, x3 is my solution vector. If I factor out an x2, I get 1/2, 1, 0. Plus, if I take out the x3 and write that corresponding vector, I get negative 3, 0, 1. And then it just so happens when we're doing these, like it doesn't matter if you wanted to go ahead and scale this by 2 so that you don't have a fraction in there. And so the basis for my final answer is going to be 2, 1, 0, and then negative 3, 0, 1. And that's okay, right? We can have scalar multiples within those vectors, and it's just a little bit nicer to write it. Oops. Sorry, these should be backwards. Multiply by 2. 1, 2, 0. Okay, and then negative 3, 0, 1. Okay, let's look at this last one. If we have A and B, just like how do we find these eigenvalues? And let's look at A. So here on A, I need to know when is A minus lambda I times x equal to 0. So I'm going to let my diagonal be minus lambda. Now, because I have 0 and 0 here, when I go to find the zeros of this matrix, then I know that like 2 minus lambda must be 0. I know that 0, I'm going to take this equal sign away here so it's not confusing. 0 minus lambda must be 0. And 3 minus lambda must be 0. So my eigenvalues have to actually be the diagonals of the triangular matrix, or like the row reduced matrix. Not all the way, okay, but that's how I'm going to find those eigenvalues. If you look at B, same thing is true. Now I have an upper triangular matrix, but if I were to do that, so like B minus lambda I equal to 0 on the diagonals there, that'd be 4 minus lambda, 1 minus lambda, and 4 minus lambda. Well, that's only going to be true, right, if lambda minus 4 equals 0, which happens twice, and 1 minus lambda is 0. So that we don't have, what am I trying to say? So we don't have an inconsistent system, right? We need those to be 0 there. So lambda equals 1. 4 would be my answers. One last thing to note here, since I do have a value, ax equals 0x, which equals 0, when lambda equals 0, which is going to be a non-trivial solution, what that's going to tell us is that we don't have an invertible matrix. So that's something really, really important to note as well.